All right, let's get started. It is 7:15. I'm Skylar Chan, and you're listening to Introduction to Reproducible Science at Technica 2023. So before we start, I just wanted to say a few things. So one is that you are free to use the contents of these slides, but they are licensed under Creative Commons Attribution version 4, which basically means if you reuse the contents of the slide and you share them in public, you also need to make your slides the same license. And this is because some of the figures in the slide have been from research published under this license. And I need to find out where my mouse is. Okay, it's here. Click. Why is it not working? Lovely. Okay, I guess there's a little bit of delay, so don't know why that is occurring, but okay, it's just fine. All right, and one other thing as well is that if you are in Zoom, I will not be able to see the questions and stuff, so I ask the technical organizers here if you can form me questions. Thank you. But yeah, let's introduce myself first. So I'm Skylar Chan. You can visit my website. And it's my name, pretty simple. I am a UMD computer science alum. I graduated in the May, actually, of this year. I'm currently a researcher at the University of Maryland Medical Intelligent Imaging Center. I have experience in many areas of research, including bioinformatics, quantum machine learning, AI medicine. And last year, I presented at Technica as well with a Linux trivia Kahoot. So this time, we're going to do something a little bit different. We're going to learn about reproducible science. First, why it's important. Second, how to reproduce science. And third, how to make my science reproducible. And this is an interactive presentation, so you're not going to listen to me talk for 30 minutes straight. If there's any questions, mark with the thinking emoji. So please take a moment to think about the questions when they come up and answer them as well if you are so inclined. And it is not loading because it's laggy. Wow, the lag is fantastic because of technical Wi-Fi. Okay, it finally decided to buffer. Yes. So on the other hand, you may also ask questions at any time. And if it lags, then we will just have to bear with it. Okay. Whew. Let's first start with what reproducible science is. So we're going to limit our talk to saying that reproducible science is going to be getting the same results with the same data and the same analysis. Right? There's other definitions of science, such as applicable, or robust, or generalizable science, but for our purposes, we're going to stick with reproducible science. I have to mash the arrow key several times for this to work. Why is that? Oh, open a new tab. Oh, I can just use the buttons here. I'll use these instead. It's a little more convenient. All right, now let's think about why we want reproducible science. So there's a lot of research out there, and a lot of it could have errors in it, right? Usually the most egregious of these papers get retracted because they misstated some part of their experimental design. But there can be other papers as well that by mistake, right, they designed their experiment poorly. Maybe they hacked the p-values to get the result that they wanted. Maybe they had a sample size that was too small, right? And we have peer review, sure, but we don't have infinite time in the world to catch every single mistake. So that's actually why it turns out a significant portion of published research is false. So we want to reproduce science, and we want to reproduce science because if you reproduce the science, right, we can review the results and say which of it is actually meaningful, which of it builds onto scientific consensus, right? In short, reproducible science makes it easier for others to verify and reuse your results. So here's an example. Some research uses Excel spreadsheets for genomic analysis. Now, Excel is probably a widely used program, so nothing could go wrong, right? Well, it turns out that there is a significant literature on how gene name errors in the spreadsheets are causing problems. So Excel converts gene names to dates and floating point numbers, which is problematic for genes like septin2, which gets turned into 2nd of September, as well as genes like this one, which gets turned to floating point number. In fact, it's not even the correct floating point number if you do the math and count the number of zeros. So why is this a problem? I would like to know. Somebody from the audience, please take a guess.
You can format that on a spreadsheet. You can format the data like whatever you want and not get it convert.
Ah, who is conducting the research? Most likely a biologist. Maybe they do not know about data types and casting, right? So if they don't have a data, if they don't have a data scientist on their team, maybe they didn't catch the error, right? Or if data was published already, right? If you have a spreadsheet of gene names already, right? And now I want to reuse that spreadsheet for my new research, right? I'm trusting that the prior team, you know, did the work to verify that these gene names are actually strings, right? Maybe maybe if I trust them too much, right, then I might propagate this error, right, if I reuse it without checking myself, right? So this is a problem because it complicates the reproducibility of genomic analysis, right? Here's a sample of papers from various top journals, right? And there's a significant portion with these gene errors, right? And so being able to reproduce the science, right, is important to catch mistakes like these early on so that they don't cause, results that are based on wrong data and wrong analysis. So let's think about how to reproduce science. We're going to use this paper to develop a good mental model for what it means to reproduce science. So Alice is an aspiring researcher and she starts a project, right? She has her data, her code. She makes her computational environment to run the scripts that she's writing. But science is a team sport, right? So Bob and Carol will contribute to the project. They'll also have their own computers and their own computational resources to contribute to the paper. Everybody celebrates because publishing is nice. And now later down the line, months, days, even years, Dan reads their paper and says, this is very interesting. I want to see how the methods work. I want to see how the results came to be. So Dan now wants to reproduce the analysis. Here's the problem. It's probably impossible for him to produce the analysis exactly. Something might be lost. Maybe the container was lost, for example, containing the code, right? Or, tomorrow is not the same time as today, right? So any events that are time dependent, right, will not be exactly reproducible, right? So the challenge is, maybe we cannot achieve perfect reproducibility. How close can we get? What do I need to reproduce science? Well, first you need an open article to understand the experimental design and methods. Then you need open data. That way you can analyze it and get some result. To do the analysis itself, you will need the code. You will also need a computational environment to host the code for the analysis. And so now let's think about how lacking each of these might pose a problem. So the paper on the left, right, Transparency and Reproducible Artificial Intelligence, they try to reproduce the paper on the right, International Evaluation of an AI System for Breast Cancer Screening. What might go wrong? And as it turns out, the original paper is missing methods and source code. Okay, so they cannot have the source code. They have to write it all over again. That itself is a big time investment. But maybe you can read the paper and look for ways that you can redo the code yourself. But it turns out that critical information to run the experiments again, in this case, the hyperparameters for the machine learning models, are missing. And so that means that they cannot replicate the experiment without just guessing, right? So what does missing methods in source code mean for the original study? I would like to know. The original paper does not report enough important details, right? Like the learning rate, for example, is very important for machine learning. It defines how quickly the machine learning model runs. If the learning rate is different, the model could achieve a totally different result, right? And so having a totally different model means that the results generated by the predictions of the model will be totally different from what's reported in the paper. So what it means, in the words of the authors that did the study, they're lacking source code, they're lacking methods, they cannot reproduce the pipeline independently. And I missed an important bullet here, but I wanted to say that the authors write that this limits the scientific impact of the original paper, right? It was not reproducible, so we don't know exactly how well the results will stand. So here's another example, right? Missing or non-identical data, right? What could go wrong? Well, it turns out data can be very finicky, right? If you don't have access to the original data, then you might run into problems. For example, data may no longer exist, right? It could be updated to a later version or removed for some reason. Data may require payment or license agreement for privacy or commercial reasons. Some data might happen very infrequently. For example, astronomical events or genetic mutations. Data could be highly noisy. Cells in the petri dish, they may mutate at any time. Quantum computing experiments, right? The measurements that you get from qubits, they are totally random. And also the instruments that you acquire the data might be difficult, right? They could be patent protected, right? So you're not able to make one yourself. And they may be too expensive or impractical, right? Because it's pretty hard to build two particle accelerators, especially when you need one right now. Right? And so I know that I expect reproducible science about using the same data and the same methods, right? But that is predicated on the assumption that you have the same data, right? If you do not have the same data, then you might have to collect your own or otherwise do some data wrangling. Like, for example, this is an important paper in AI medicine because it hints at the idea that medical data has been biased, thus causing models trained on them to be biased, right? Now, this paper has something happen to the data in it. So what might go wrong with the data used in the paper? Take a guess. That is correct. This data was updated. The original data used in the paper, Mimic version 1, no longer exists. Okay, I'll use Mimic version 2. But wait, this version irreversibly changed the labels. You cannot use the labels in version 2 to get back the labels in version 1. All the patient identifiers changed as well, which means that it's impossible to reproduce results exactly as represented in the paper. Now, this paper is still important because it gives some good theoretical ideas for research. However, if you want to look at the results of the paper, unfortunately, because we cannot reproduce the results, that limits our ability to do cool new analyses with them. And here's one more example. I will disclose that this paper is authored by a research lab, and I actually have been working on producing this paper as part of my work. So what might go wrong in this paper when I try and produce it, right? This paper does pretty much everything right. They have an open article, they have the source code, they have all the data. But what they are missing is the environment. You know, they report the version numbers for Python, PyTorch, scikit-learn, right? The big stuff. And so I need to recreate the environment, right? Because they haven't told me every single little dependency that I needed, right? They didn't provide me an environment, the text or some other information that captures that. However, it turns out that the versions they report, you cannot download them from Conda anymore because they have been flagged with security errors. Now, normally we care very much about security. However, in science, that is sometimes something that we will sometimes have to compromise in order to get the results we need, right? And so you can say, well, I'll just update the dependency to the closest possible version. But what this means is that now I'm using software that is totally not identical to the software that was used in the paper, right? Any one of the dependencies could have changed the default value or the API that could have caused some number to go wrong, to be calculated in a different way from the paper. It goes further. It turns out the PyTorch model used in this paper is hard-coded to the latest version, specifically the main branch of the Git repository, which means that the version of the model I use today, if I were to reproduce experiment, is different from what's published in the paper. And it also means that if I reproduce the paper tomorrow, that will be different from the paper. That means the results I reproduce tomorrow will be different from those I reproduce today, simply because the model is different, right? So at least this has a good ending. At least the results are correct, subject to rounding errors. But what if? What if one of these dependencies actually had an ABI change or an API change or something changed, right? Then that could be disastrous. You know, it could be more than a rounding error. It could be a sign change, right? Then that would have big implications for what I can do with the results. Okay, so we've gone through some examples of, what I need for reproducibility, right? So let's figure how I can make our science reproducible, right? And this is a hackathon, right? So if you have a reproducibility project, you might have a lot of time, right, to make a result perfect, right? But we can think about what we might need, right? Do we need our results to be similar? Like, are rounding errors okay? Or do I need every single decimal digit to be the same, right? Because that is going to matter, um, later on the line. Similarly, do you need a specialized hardware, such as a GPU for quantum computing or machine learning experiments, right? Not everybody will be able to access the same kind of hardware, right, that used for the experiment. How long do your results need to be reproducible for? If I need results to be reproducible tomorrow, I can probably get away with a little bit more leniency. If I need them to be reproducible years, decades from now, then I might want to be a bit more careful, right, in how I construct my reporting. Finally, can I download my data, my code from the internet? And you might say, well, I'm watching this presentation on Zoom. I'm using the internet right now. Fantastic. That doesn't mean that the code and data will be at the same URL forever and ever, right? You need to account for this sort of thing, perhaps. So it's also important to document your methods, right? And I will mention that correctness is more important than reproducibility. Question.
Can you go to the slide back?
Yes. Let me do that. real quick. Yeah, all the slides are publicly available at the end, so you may reference it at any time after the presentation as well. But I just want to say that correctness is more important than reproducibility because you can always reproduce an incorrect result, right? So if you're time limited, the most important thing you can do is make sure your methods are correct and documented, which means one, using literate programming. You can combine your code with documentation. Use Jupyter for Python scripts, R Markdown for R scripts, Jupyter for R scripts, whatever, right? Explain what your code is doing, right? You can use descriptive variable names instead of using single letter variable names. Is it variable A or B? Well, it could be, average model accuracy or balanced class accuracy, right? You can track your code changes with the version control system as Git, such as Git, right? So you can watch your code evolve over time, and you can share your code methods online, for example, with GitHub, that we can share your work with others when you're finished. All right, another thing that's important is to control for non-determinism. And this is what I'm talking about with regards to the example where the model may change over time, right? You can set random seeds for deterministic random number generation. So I get the same random numbers every single time I run it instead of getting different random numbers, right? You can use relative paths instead of absolute paths. For example, you can on Linux, you can reference home on any computer instead of using the root directory, and it only works on my computer, right? And what if a URL you need is not available anymore, right? Like, what if the model I need, I cannot download from the internet anymore? What if the package I need is not there? Then that's a harder problem. And you know what? This is a hackathon project. Why not you give it a try and tell me? Because I would like to know. This is a very hard problem. Another thing as well is to use a package manager, right? So, you shouldn't compile and install source code by hand because that's very tedious and probably error prone. You should use a program that will download other programs for you. Yes, it does sound very silly, but the advantage is that you can create a file that has the list of all the packages you need and all the versions you need, right? So here it uses the experimental geeks package manager, but you could do it with Conda as well, right? And if you're thinking, okay, maybe I want to internet in the future, right? Then what you can do is you can throw all your dependencies into a Docker image or a virtual machine, right? Or some other containerized solution, right? So instead of people having to go to the internet for maybe hundreds of dependencies, they can simply download your Docker environment, right? And say, I want to download one thing instead of many things that could each go missing. And I just want to end by saying software versions are not enough, right? So let's say, my experiment, I'm using version R, I'm using R version 4.1.1, right? Now, how many packages do you think R depends on, right? Surely I'm only using one software, right? Does anyone take a guess, a ballpark, how many numbers? More than 100? Okay, good guess. It turns out that we need at least 304 dependencies. So you're not using only R version 4.1, using R plus 300 different other software versions, right? Or 304 different softwares with different versions, right? So it's hard to see on the screen, but let me read some here. We have util Linux at 2.35.1. We have doc.xxl at 1.79.1, stuff like that, right? So, what this means is that the more complex your software stack grows, right, the more dependencies you have, and the higher risk you'll run that any one of them will randomly change a default value, an API. They might refactor the function so it requires 3 arguments instead of 2, right? That increases the chance that you're going to have something that will cause problems if one of those versions changes in the future, right? And so it's not only enough to record the software versions, you should also record the environment details, right? At least tell us what operating system you're running on, right? If you're running on Linux or if you're running on Windows, that immediately gives us information about what compiler and C library was I using for all these packages, right? What is the build toolchain that I need to get all these softwares that I need to reproduce study. And you might say, Skylar, that's great, but I have a Docker image. I can just download a Docker image for free, right? And you know what? That's true. But think about it. Docker is software. It's software that has to be compiled, right? What operating system was it compiled on, right? And so you're back to square one, right? Docker is software. You still need to describe how the Docker was created, right? And additionally, you will still also need to provide details on how the Docker container itself was created, right? And the level that you describe it at can depend on your experiment. But the point is that because everything needs to start from the operating system, right? At least tell us that. At least tell us that. And again, you can capture all the information about all your dependencies using a version file, right? A file with all the versions. Question.
There is no end to this, right? If you're putting like, you're saying Docker version changes, operating system changes, then what are we trying to achieve? I'm trying to understand.
Yes, that's a good question. And And actually, there is an end to this. In some of the further reading I've attached there, it's a project called the Bootstrapable Builds project that aspires to compile everything from a readable binary hex seed. Now, that's probably too much for most people, right? And so what we need is a higher level of proof, right? So, and that's how I'll end the talk by saying, well, I'll come back to this later, but to continue answering your question, I'll end the talk by saying that, let's see, you can at least record the environment details, right? Because this is simply recording the environment details, all the package versions and all the package names as an operating system will already get you very high in terms of reproducibility. Because as many studies in reproducibility among research has shown, most papers do not even do the minimal amount of work, right? Because all you have to do is run one command, pip freeze, content env export, one file, done, right? For certain analyses that, let me get back to here again. For certain analyses that do require very high precision reproducibility, right? Then sure, it is good to describe, in more detail all of the stuff, right? And we can debate on whether it's overkill or not, but this is part of research, right? It's how reproducible can we get, right? Your needs for reproducibility may depend on what field you're in, right? So, for example, the reproducibility I'm going to use for say my bioinformatics experience may be different than the reproducibility I'm going to be using for my quantum computing experience, simply because they're different fields, right? And so that's what I would say is that surely there is actually a definitive end to this chain, right? But for most of us, right, if we do even a little bit, that is already a lot, right? And so actually, I wanted to say if you need a hackathon idea, I have one for you. You can find a study. For example, I found this Nature paper for my AI and healthcare class. You can reproduce a study. I reproduced a study by using a different programming language, right? I used Python instead of R, right? Because I wanted to say, okay, maybe the implementation will be different and the results will change, right? So technically, this is a little bit different because the methods are different, right? But regarding that point, and then you can ask yourself, how reproducible is the study? Can you get the same results? And maybe you can do a little report on that, and that would be pretty cool. But yes, to repeat the too long didn't read because if you fell asleep, I'm very sorry. Maybe I was too boring. But it is now time to wake up because reproducible science is important. You can double check scientific results and build scientific consensus. You can reproduce science, use the same methods, data, code, and environment to get the same results, or at least as close as possible, because that might not all be possible, right? And you can do some best effort reporting, right? You can write down your code and share your methods, code, and data. You can make your code non-deterministic. You can record your environment details. This already will bring you to a very high level of reproducibility. And editors at journals will be very pleased with you. And as I mentioned, there is a rabbit hole for reproducibility, right? There's lots of directions that you can read about if you're interested in studying this further. And then, yeah. So hopefully you have learned that reproducible science makes it easier for others to verify and reuse results. And with that, I'm happy to take any questions.
The problem statement that you're trying to make, okay, it's applicable in the research that you're doing. What is the applicability of this? Like, I work in IT industry. Okay, I have I work with government data. Okay, lot of data. Most of them reproducibility ends at the data set. Okay? It's not like version control of software because the data is not. Data is the main aspect that you wanted to get to the right thing. The research that you are doing right now, or what you are describing about, what are the usability factors of this research that you're doing?
Yeah, that's a great question. And I wanted to start with saying that you mentioned you work in IT, but IT is a very different field from science, right? In IT, you may have less strict reproducibility requirements, right? Reproducibility can help you with your continuous build integration, right? So that you can say that, because as I mentioned, many of the steps that I use for how you can make yourself reproducible also happen to apply on how can I make my software stack sustainable and maintainable, right? Because, if you can record all the data environment, that means that's less for somebody to have to extend that or reproduce it on another machine. But I digress. The important point about this is that in science, right, to build consensus, right, we need to review the results and we need to say, based on the methods, right, and how the methods apply to the data, did they get the result that they wanted, right? And if that happens to be true for enough papers, right, for enough research, then we tend to agree, there's a body of evidence that supports this, right? And so this is what reproducible science is about. It is one part of building that evidence, right? Because if we can say that, look, we have the data, the code, the methods, and the environment, and we have the results. That means that it was possible to independently reproduce the results of the paper, right? Independent reproduction of results is a very important part of building evidence for a scientific foundation, right? And this is what I was referring to earlier, actually, um, with this slide, right? So I think let's review this slide again, right? So this paper was actually the international evaluation for ACEs and breast cancer screening, right? This paper, I'm sure, was very big news when it was published, right? Otherwise, it wouldn't have attracted the paper to try and produce results, right? But because the results were not reproducible, right? Why is it not working? All right, because the results were not reproducible, right? Let me see. Let me actually try and, I know you won't be able to see it on Zoom, but let me try and find you the slide that I had this on. Let me try and undo some things here. Okay, I guess I cannot find it this time. Unfortunate. But what I was going to say, that one of the things that I did not mention here was that the authors in the reproducibility study, they mentioned that because the paper is not reproducible, this limits the utility of the established literature, right? And as I mentioned, right, because most of the literature is false because it has reproducibility issues, right? A lot of machine learning experiments, for example, and I know I'm being specific to machine learning on quantum computing and bioinformatics and whatever, but reproducibility has been documented across pretty much every scientific field out there, right? If they lack the source code, right, then you have to write all the code from scratch again. This makes it difficult for you to reproduce results, even if they provide the data for you, right? Even if they have the source code, there can be multiple issues with you trying to restore the environment to get the same results again, right? And so this is why reproducible science is important, specifically for science, right? Because it's an extra way for you to build consensus, right? For IT, again, it's a different story, just simply because the needs are different, right? As scientists, we build tools to solve problems in science. And I assume in the same way, in IT, we build problems to solve problems in IT, right? So I hope you understand that this is an issue that's becoming more and more important. Any other questions? Yeah, so let's check the time here. It's 7:42, so actually we are just right on time. I will go back to the reproducible rabbit hole page. Actually, let's not do that. Let's go back to the main slide. Oh, we can leave it up. Yeah. So I'll just quickly, in the last few minutes I have, just quickly go over the rabbit hole here to show you some of the bleeding edge directions, right? So prior work essentially has been focused on improving package managers, right? Because package managers may have limitations that prevent them from expressing the computational environment effectively. For example, Conda is very slow, right? And also has some inherent design decisions, such as not being able to permanently archive versions of software, right? So one such project, which I mentioned, could be your hackathon project. Some engineering team has done this, is software heritage. It's a backup service or code storage. So you can archive scientific experiments, results, and code. So that way in the future, all you have to do is similar to how you reference a DOI, digital object identifier, you reference a SWH, software heritage identifier, right? So think of DOI, but for code, right? Here is a textbook that you can consult online. You can read in bits and pieces for how to do reproducible research. And as I mentioned before, Bootstrapable Builds is a project to see how small can we go, right? From being able to bootstrap everything from source. We also have the probably more practical reproducible builds where it's simply, can we achieve bitwise reproducibility, at least in the software versions, right? So if I compile my thing on machine A and I compile my thing on my machine B, the results should be the same. And then finally, here's a more detailed report from the Geeks High Performance Computing Project on how you can achieve reproducible research papers. But I believe I've overshot my time. Oh no, it's 7:44. So we will also end right on the dot. Thanks for your attention. Happy hacking.